Hello, I'm Omnik. Today I will be solving second division at the first round 907, and I will try to explain what I'm doing. Let's go. Or not. That's slightly longer wait than usual. Problem A, sorting with twos. Have an array of integers. Choose non-negative integer m. So basically we're choosing power of 2. Right? Subtract 1 from first 2 to the power of m integers. Can you sort the array in non-decreasing order by performing some number of operations? We are allowed to make elements negative, right? Why it's not mentioned anywhere? Well, I guess we should be allowed. So basically we're just given that on some prefixes with length power of 2, but that's not really important. We can do -1 on that prefix. But if we look at like how does it change comparison between consecutive elements, so we want the whole array to be sorted, and to achieve that we need to make sure that every pair of consecutive elements is correctly compared, correctly sorted. But that's also enough. So it's necessary and sufficient for if we want array to be sorted, we just need to make sure that every 2 pair of consecutive elements is correctly compared. And if we look at difference between 2 consecutive elements, then if we both like subtract 1 from both of them, then the difference doesn't change. If we don't subtract 1 from both of them, the difference doesn't change. And only if we subtract 1 from one of them but not from the other, then the difference will change. So we can only like the only pair of consecutive elements that will be affected by the operation is the one like on the border between the prefix on which we are subtracting and the suffix on which we are not. And basically on like for those pairs of elements that are on the borders, we can make the first element to be smaller than the second one, always. Just by subtracting it until it becomes smaller. So basically we need to look at all the other pairs of consecutive elements, the ones where we cannot do anything, and they must be already correctly sorted, correctly compared, because we cannot change that. And if all of them are correctly compared, then we can sort the array, otherwise we cannot. So the solution is like we iterate over all the pairs, and either this pair can be changed, so like we need to check if the left one is like the index of the left one is the power of 2, and we need to remember that it is like in one indexation, or that they are correctly sorted. If both of those things are not true, then we cannot sort the array. If for all the positions it is true, then we can. Technically, we don't need to store the whole array. But if we don't read the whole array because of multitest, we cannot just break after we found bad pair. We need to read everything still. So I will read the first element and then n-1 times. I will read the second element, check if the criteria is satisfied, and then assign x to be this element, so we can compare it with the next one. And the condition is that either the previous element is smaller or so the index of the left element in one indexation should be a power of 2. The other way to look at it is the index of the right element in 0 indexation should be power of 2. In any case, this I that I have should be a power of 2. And when we want to check if some number is a power of 2, we can take bitwise AND of this number with this number -1. And if it is not a power of 2, then the highest bit of those two numbers is the same, so the AND will have this highest bit. And if I is a power of 2, then this will be 1 and a lot of zeros, and this will be 0 and then a lot of ones, so their AND is 0. So this function kind of checks if the number is a power of 2, but it only works for strictly positive integers. You can see that if the number is 0, then this is still true, but 0 is not a power of 2. Okay, I guess we can return else. So they ask with caps. Usually in converses it's fine to print not caps, but it is not set here, so I'll change it. Problem B, déjà vu. We have again an array of length n consisting of positive integers and an array x of length q. There are q modifications. So, on the ice modification, for each j such that this element is divisible by 2 to the power of xi, you add 2 to the power of xi minus 1 to aj. Xi is a positive integer not exceeding 30. Okay. After all modification queries, we need to output the final array. Okay, so basically, if we're looking at the binary representation, if the number has at least x zeros in the end, then we change first of those zeros to 1. So the only thing that can happen is changing some 0 to 1. And those changes will only move like to the smaller bits, because we do the change only if like in that position and on all positions to the right they're all zeros. So what will happen to the number depends only on like what was the number of zeros in the at first, at the start. So there are only like 30 options. We can for every such option we can just run the algorithm, run all the modifications, and then we will know what will happen in the end with such number. Then for every number we will, in the initial array, we can determine its type initially and apply the modification. Well, okay. It's a problem, I guess. So the solution is iterate over how many numbers, how many zeros we have like after the last one bit in the number initial. And then we're like, okay, currently the last one bit is in k and it will change during the operations, so we iterate over the operations, and if the next operation is applied to the bit strictly smaller than currently the last one, then it means that on this bit and on all to the right we have zeros. So we will change this bit to from 0 to 1. I guess not this bit, but like 1 less than this bit, right? So I want to minus u. And I will just remember that I'm setting this bit like adding 2 to the power of car for those numbers. So now for every possible number of zeros in the beginning, I know what I will add for each such number. Now I just iterate over the numbers, determine the type. So the stupid way to do that would be to do something like this. So while k's bit is 0, we increase k. It works in logarithmic time, and it's not like bad for our purposes. We already spent like log set times m operations here, but it can be done, I think, in constant time with built-in function. So I think that it should be like built-in count trailing zeros. Looks fine. Problem C, Smilo and monsters. There are n hordes of monsters. The ice horde contains AI monsters. So we are given an array of integers. The goal of the game is to destroy all the monsters. To do this, you have two types of attacks and the combo counter x initially 0. So the first type of attack, choose a number I from 1 to n, so basically just a monster, so that there is at least one monster left in the horde with the number I. Then you kill one monster, and the combo counter increases by 1. So you can do minus to one element that is strictly positive, and the combo counter increases by 1. The second type, I guess, like use the combo counter, we choose an array, so that there are at least x monsters, then use an ultimate attack and kill x monsters from that number. After that, x is reset to 0. Okay, makes sense. Your task is to destroy all of the monsters, meaning that there should be no monsters left in any of the hordes. Smile wants to win as quickly as possible, so he wants to know, I guess, the minimum number of attacks required to win the game. Was it fixed? No. Okay, so we have an array of integers. So we kind of have these blocks of attacks, right? We like increase combo counter and then spend it. So if we want to have an ultimate with power k, we will spend k plus 1 attacks. And first k will be of the first type, so it's k attacks of 1, and then 1 attack of damage k. So kind of like every attack of the first type like should decrease the total health kind of by 2, like by 1 through the attack and also by 1 through the fact that it increases the combo counter. Except that like maybe in the end we will have attacks that do not contribute to any combo. So kind of the number of attacks of the first type is fixed. It's just total health of all the monsters divided by 2, rounded up, I guess. And we want to minimize the number of combo attacks. So less combo attacks means that like every combo attack should be big. So it kind of makes sense to spend combo attacks on big monsters. So let's say that we are going to use M combo attacks. So let's take M highest by health monsters, and so this first combo attack we are going to kill the highest by per monster. So we spent like attacks of the first type on low HP monsters, and then with one combo attack we kill the highest HP monster, and so on. So the minimum number of combo attacks we will use is equal to like minimum number of monsters we need to apply combo attacks to, but like we know that combo attacks kind of take like they should take half of all health points of all monsters. So we just sort the monsters by decreasing a level of in decreasing order of their health points, and we want to find the minimum prefix such that the total health of monsters on that prefix is at least half of total health points, except like if the total health points are odd, then there will be unpaired attack of the first type that we must do it. So that half it is rounded down. So the answer to the problem is total health divided by 2 rounded up plus the smallest the length of the prefix after we sort in decreasing order, the length of the smallest prefix such that the sum of their health points is at least total health points divided by 2 rounded down. That's a nice problem. Very decent. It's not even a play. Unusual. Okay, so this solution works in n log n because of sorting. I guess it's technically possible to do in linear time. If we, like, instead of sorting, we can try to do something similar to nth element in linear time, except that we don't know like what's the position of the element that we want. We're actually trying to find it, but we still can do something like choose a random element, do the partition, calculate the sum of everything that is like up to this element. If it is not big enough, then we need to solve recursively in the larger half. If it is big enough, then we need to solve recursively in the smaller part. So that will be O of n on average, and I assume that you can do something similar without randomization, but yeah, that's like more of a theoretical thing. I mean, it will be faster. It is like it would be actually linear time, but it is not needed in this problem, obviously, and like it would be hard to come up with a problem where something like that is needed. But theoretically, it is linear, which is nice. Problem D: suspicious logarithms. Let the plane flight. So we define function f, the floor of the binary logarithm of x. Largest non-negative integer y such that 2 to the power of y does not exceed x. Okay. G of x be the floor of the logarithm of x with base f of x. Sure. You're given q queries, and you need to find the sum of this function g on a segment of numbers, and numbers are big. Well, I would guess that function g of x is monotone, like non-decreasing. Maybe it's not true, but it should be kind of close to be true. Maybe there are like just small number of segments with the same value. So basically f of x slowly increases and it's monotone, and the largest value in our range would be like 60. And then for fixed f of x, okay, yeah, for fixed f of x, g of x is obviously increasing because f of x stays the same. So the logarithm with fixed base of increasing numbers will be increasing. So that means that there are at most logarithm like sub-segments of every segment of constant f, but actually like for a segment with constant value of f, the left and right border are only different by like in 2 times, right? Like we jump from one power of 2 to the next power of 2, not inclusive. And so when we take logarithm by some base that is at least 2, those values cannot be much different. Like they can differ by at most 1, actually less for smaller bases. So their floor values can either be all the same or like can only have 2 different values. One that is smaller, and then at some place it will be one bigger. So we can find all those segments, and so we need to find the place where the value changes, but that's basically like if the value in the left border is k, then it will be k until we arrive at f of x to the power of k plus 1. So just find that number, and if it is on the segment, then it splits into 2 smaller segments with different values. So now we have divided all the domain, or all the possible axes, into at most 2 logarithms segments. On each segment the value of the function g is constant. So for each query we just intersect this given segment with all the segments we have and calculate the sum that way. They asked me to print modulo 10 to the 9th plus 7, but I'm pretty sure that the answer would, well, if not fit in long, then like it should fit in unsigned long. Should be true. So like all of the g values are like at most what, like 15, 16, and 16 times 10 to the 18th fits in unsigned long. So because we have just like 2 logarithm segments, we can iterate over all of them for each query, but technically it is not needed. Like we have those segments, we can write them in just one line, like in an increasing order of the values. Then we could calculate the sums on every segment, like if we take the whole segment, and calculate prefix sums on that. And then for a query, we could find at most 2 segments that like are not fully inside the query segment, and for everything that is fully inside, just take the sum from the prefix sums, and on the borders calculate the sum by hand. So that would be like for each query logarithmic from the number of segments. So if it would be like 10 to the 5th, 6th, still would be fine. But we don't need to do it here because the number of segments is actually much smaller. So our x starts from 4, so logarithm starts from 2. We can iterate over the value of f of x from 2 up to 60. And so the left value is 2 to the power of k, the right value, not inclusive, is 2 to the power of k plus 1. So now we can find the value of g. So this is the value of g. Let's call it like g left. And let's find the value of g like after our segment. And if they're not equal, so if they're equal, then just on the whole of this segment the value of g is equal to this, and so we add just one segment. From left to right. Otherwise we can calculate k to the power of gr to find the first number on which the value function g becomes bigger. I want to check my insane hypothesis that the answer fits in unsight long clone. So I'm intersecting the segment of the query with my segment. I did R++ to make it like half interval. Okay, yeah, let's make this one just one clone. Interesting. Oh, like I should start with like -1. Looks right. So this one is almost max test, right? 69. So it's a bit less than 10 to the 19th power. Does it fit in? Yeah, it doesn't fit in side long long just by a little bit, but it fits in inside long long. Problem E. An exams difficulty AI, which is a non-negative integers, ever given an array of integers. Looks like it. Milo doesn't like when the greatest common divisor of the difficulties of two consecutive exams is equal to 1. Sure. Who would like that? Therefore, he considers the sadness of the academic year to be the number of such pairs of exams. Okay. Wants to minimize the sadness. Can set the difficulty of any exam to 0. So basically, we remove this exam and make like both consecutive pairs to be good. Except if like, one of them has 1. Okay. He doesn't want to make his students' lives too easy, therefore he will perform the section no more than k times. Okay, so the problem is we are given an array of n integers that can be 0, non-negative. We can change at most k of them to zeros. We want to minimize the number of consecutive pairs that are k'. Okay. If no elements were equal to 1, then changing one element to 0 makes both pairs containing this element to have GCD greater than 1, or like 0. So basically, we have elements that are 1, they are like strongly making everything near them coprime. Unless we make this element to be 0 itself. And for all other elements, we just care about like whether there are coprime pairs near them, because we can like take this element and make both pairs around this element to be not coprime. So how does that look like? We have some elements that are ones. And we have some elements that are not ones. Can also have like consecutive ones. And also for some pairs of elements, like for all pairs containing 1, so those are coprime pairs. But there can be other coprime pairs. So maybe this is coprime. Okay, and the operation is to choose an element to make it 0. I think that we are interested in groups of consecutive ones, and also like after we remove every such group with both pairs adjacent, like on the left and on the right. We are also interested in this segments of consecutive pairs, prime pairs. So those segments are easy, like we can remove 2 pairs by changing one element. So if we have like this long sync that are one segment, then we can make this element to be 0, and that removes like this two. Then in the next operation we will make this element to 0, this removes this two, and so on, until we are left with just one element that we can remove with one operation. So at first we can have operations that remove two, and if the length was odd, then we can have one more operation that removes one. Okay. With ones it's a bit trickier, I think. So if we have a lot of ones, we will also have bad pairs here. There can also be a like very nasty case where this one is at the right end and there is no pair here, so removing this one is kind of very bad. Okay, let's first talk about this case. Well, it seems that if you change all ones to zeros, then you remove all the bad pairs, which will be like their number will be one greater than the number of operations we do, because of if we start on the left, we like remove this one, this one, this one, this one, but then in the last operation we remove both pairs. And it seems that we cannot do much better than that. Like if we just change some ones to zeros, then like in the middle, basically we're freeing only pairs that are between zeros or like on the outside. But basically, until we can remove all the ones, we cannot free more pairs than the number of operations we spent. And we can always just go left to right, and in every operation we will free one pair. Except in the stupid cases where there's one at the border. Well, we still can go like from the free side in the opposite direction. In every operation we will free one pair, but in the end we will not get one pair for free. And there is like a case where everything is ones, so like both borders are bad, and in first operation we cannot free any pair anyways. And well, after that we will get into the situation where we have at most two those like segments of ones that are bad on one side. So like we have to Yeah, we have to spend one operation in vain. But then we will get one free pair for every operation. Okay, I guess it is easier to just like hard code this case where everything is ones. Just the answer is maximum of 0 and k minus 1. And k is starting from 1. So okay, we have k operations, we need to spend them wisely. How do we spend them wisely? So there are like segments of pairs without ones where it's always good to remove pairs because we cannot get more than 2 pairs free in one operation. So we start with them, and after that we will have some groups of ones where we can spend the size of that group number of operations and like get one free pair. So for every operation we increase the score by 1, or like reduce the number of bad pairs by 1. But if we finish the whole group, then we get 1 for free. So we want to take smaller groups. Well, that's basically it. Yes. So we start by for every pair of consecutive elements we calculate GCD, check if it is 1, then we find all those segments. Start by removing 2 while we can. That's while we have them, or while we have the operations. I mean, both. And then find the groups. Calculate the maximum number of groups we can take just by sorting and taking the smallest groups, kind of similar to problem C. And like all the remaining operations, we will reduce the number of bad pairs by 1 for each operation, but also for each finished group by 1 more. And there is a special case where everything is 1. Actually, interested if there is such sample. There is, so they're generous. Okay, so I think I can start by finding all the groups of ones, keeping in mind about like borders, and in the case when the group has two borders, so all the ones there. Maybe it's easier to just actually hard code it. There still will be an if, so okay, let's just hard code it in the beginning. So the answer is n minus k. Well, technically it should be like maximum of k and 1, but k is at least 1. So in the beginning all the pairs are bad, so there are n minus 1 of them, but on the first iteration we cannot reduce the number, but then we can. And k is up to n, right? Okay, so now I want to find all the like segments of ones. Their sizes I will put in this vector, and after I find a segment and record its size, I will just set all those ones to zeros, so that they don't create pairs of k-prime elements when I will work through getting all the segments of k-prime elements that are not ones. Also, I think it will be easier if I just initialize the answer in the beginning. So this if is needed, I think, because the built-in GCD function doesn't work when both inputs are zeros. I'm not sure, but I think it doesn't. Found segment of ones. If it is not on either border, then in B I should put the size of that group. And now replace with zeros. Now similarly find the segments where like every consecutive pair is K'. I guess I should just write my GCD so that I don't have to put this check every time. What am I doing? So up to this point, what is the number of pairs? Well, it should be this. And so for this divided by 2 rounded down number of operations, I can reduce the answer by 2 for each operation, but I should also take minimum with the number of operations I have left. And so now I can take, I can make X operations, each of which will reduce answer by 2, so I reduce the number of operations available by X and answer by 2 times X. All right. So now for all the remaining operations, I will reduce the answer by 1, at least. But also for groups that I can make fully. And to spend X operations on that, and I can get 1 bonus decrease for the answer. But after all that, like, considering that here I could have decreased answer by 2 or more, it could happen that my answer became negative, which is not possible, obviously. Wow, it's incorrect in 2 places. Amazing. The last case is this one. But I only should have one group focus. This and this on the border. Oh, should be. Strong samples. Problem F must be some kind of data structures, right? Yay, data structures on tree. Great. You are given a rooted tree with the rooted vertex 1, initially consisting of a single vertex. Each vertex has a numerical value, initially set to 0. Q queries. First type, add a children vertex with number size +1 to vertex V. Numerical value is 0. Okay. Add x to the numerical values of all vertices in the subtree of vertex V. And it is offline. What's the problem? Can't I like construct the whole tree, build a segment tree over Euler order, then like add on subtree just by adding in like on a segment? But then like I will add in vertices that are not created yet, but when I create the vertex I can ask for the current value there and set it to 0 by hand. That is not the last problem in second division. I guess it's just like an easier round overall. Well, okay. I don't even need segment 3, I can do it with Fenwick. Like, yeah, I need to add on segment, but I can add in the beginning and subtract in the end. Is there anything easier? Well, I don't know how much easier is possible. Like this is very easy already. Even if you just have the tree constructed and then add in subtree. Well, I guess you could deal with just DFS. Because you only need to output in the end. I don't think that there is anything much easier. Is it solvable online? Probably. With link-cut trees, it's surely solvable online. Without link-cut trees. Well, what is unline? Like, I just need to output in the end. Like, unline in terms of I have to be able to answer the value at the vertex at any moment, but that's a different problem. Still, like, should be doable with linked trees. But whatever, let's just write simple thing and be done with this contest. Okay, I will need fanfic, and that's it. Yes, I need to clear carefully because I don't know the size of the tree. Oh, I can just clean up to the number of iterations. Right. Okay, that works. I also need to store the updates. So if it is -1, then it means that I create new vertex, and if it is not -1, I should add on sub3. So the vertex is A0, and the subtree is well, the segment is TV0, TV1, and so I add TV0, AI1, and after the end of the segment I subtract the same. The vertex is A1, the point is TV0. I need to get the value at that point right now and subtract it from that point. Yeah, that is way too easy. I mean, I spent a lot of my time on E because I was explaining the solution, like I understood it fast enough, but still, E is much harder than F. I mean, they're different, like in F you need to know about the existence of Euler order and like how to do the operation on subtrees. And I guess about the existence of offline algorithms, but like they only ask everything at the end. Why would you even consider doing it online? Yeah. Problem F does not satisfy my notion of what should be the last problem in second division. Like, this could be Div1A. I mean, it couldn't be because it wouldn't be accepted by the coordinator. I hope. But just from difficulty, I mean, yeah, there's much more solutions than E. Like, closer to D. Probably, like, it's smaller than D only because it is on position F and many people do not check like standings or dashboard or something and just solve the problems in order. But yeah, I guess F is easier than D, which is also not a hard problem, but it looks scary, at least, like massy. So I guess I like problem C. Problem C is nice. Those problems. I don't like this, but like, I'm not the person to judge Div2A's. B is fine, actually. Yeah. I even think that my solution is a bit hard for B. Maybe there is something simpler. Like, probably you can just notice that you only perform operations with like decreasing values of x, and so from each value from 1 to 30 you only need the first one, and then you have just 30 operations and you can implement them. But it's not very different from what I did, actually. I guess it means that my solution could be like n plus q plus log squared. Probably you can do even better than that. Just by saying that you can apply the operation only if all the previous operations are strictly bigger. So you will have like this decreasing sequence and you only need to apply a suffix of it which fits, but that just means that you can put all the operations in one mask and then solve every position in constant time. And it's kind of cool. Yeah, still, like, I like problem B. Okay, I like problem C. It's smart. The idea that every attack of the first type actually gives 2 damage, because like 1 right now and 1 from the like future combo attack, future attack of the second type is very nice. And then like it shifts from like you're doing some weird operations to like the attacks of the first type just give you 2 damage, and the attacks of second type don't give anything, but you cannot just use attacks of the first type. So you need to minimize the number of attacks of the second type, and then the solution is also nice. Well, yeah, problem C is certainly the best problem in this contest. D is fine. It's not super interesting. It just looks scary, but it's fine problem. E is a bit like KC. But I guess it's an okay problem. But there are a lot of cases you need to consider. And it's easy to forget something. But I guess like the sample is very generous. And F is like educational problem and queries and subtrees, and like the existence of offline algorithms. Yeah, did not expect that from problem F. Maybe the intended solution is harder. I don't know. I don't think you can reasonably say that F is harder than E. That's just not true. Like, you probably can say that F is easier than D. F is harder than D, but not by a lot. But certainly F is easier than E. So maybe the intended solution is different. Maybe they are doing something online. Maybe they wanted to force online, but didn't see how. And like, if you only ask to output after everything, how can you force online? It's just impossible. Very weird. Yeah, and I don't understand how problem F got on this position. Like I guess it's okay problem for second division. I get a lot of flack for saying that all the problems in contest must be like new and original, and people are saying like, people in Div2 like don't care about that, and they need to learn the standard things from somewhere. Well, I don't agree that they should learn them from contests. But I guess like I can understand that this problem can exist in second division, not on the first one. No way. But not on the last position. Well, okay. Thanks for watching. Bye.